Tellegens theorem is one of the most powerful theorems in network theory. Most of the energy distribution theorems and extremum principles in network theory can be derived from it. It was published in 1952 by Bernard Tellegen. Fundamentally, Tellegens theorem gives a simple relation between magnitudes that satisfy Kirchhoff's laws of electrical circuit theory. Bernard Tellegen, a Dutch electrical engineer and inventor, published Tellegens theorem in 1952. Tellegens theorem is the most fundamental network analysis theorem from which most other theorems are derived. Having an understanding of this fundamental theorem will help us to understand how physical impedance functions function. Tellegens theorem can be applied to lumped systems that consist of linear, active, passive, and time-varying elements. Likewise, this theorem is convenient for networks following Kirchhoff's voltage and Kirchhoff's current law. The Tellegen theorem is applicable to a multitude of network systems. The basic assumptions for the systems are the conservation of flow of extensive quantities, Kirchhoff's current law, KCL, and the uniqueness of the potentials at the network nodes, Kirchhoff's voltage law, KVL. The applications of Tellegens theorem revolve around synthesizing power in electrical networks. Some practical applications of the theorem are listed below. The theorem is used by digital signal processing for filter design. This theorem determines the stability of complex systems in chemical plants and the oil industry. The theorem is used in reaction network topology and structure analysis. Steps involved in Tellegens theorem. Using Tellegens theorem can be broken down into a few simple steps. The steps are as follows. Step 1. The first step is to identify the number of branches in the given electrical network and then calculate the power dissipated across each branch using a conventional method. Step 2. We can find the instantaneous power of each branch. Step 3. There are two branches: power delivering branches and power absorbing branches. We have to identify the power delivering branch and the power absorbing branch. Step 4. It is appropriate to assume a positive voltage drop in the power delivering branch and a negative voltage drop in the power absorbing branch. Of course, the signs can also be reversed, but whatever the convention should be carried throughout. Step 5. All power calculated from all branches must be added to justify Tellegens theorem. This sum must always be 0. The Tellegen theorem provides a useful tool to analyze complex network systems including electrical circuits, biological and metabolic networks, pipeline transport networks, and chemical process networks. Tellegens theorem states that the summation of power delivered is 0 for each branch of any electrical network at any instant of time. It is mainly applicable for designing the filters in signal processing. It is also used in complex operating systems for regulating stability. It is mostly used in the chemical and biological system and for finding the dynamic behavior of the physical network. How are KCL, KVL and Tellegens theorem related? The consequence of Kirchhoff's laws like KVL and KCL is Tellegens theorem. This theorem is verified through KVL or KCL. Can we verify Thevenin's theorem both on AC and DC circuits? Yes, we can verify Thevenin's theorem both on AC and DC circuits. Similar to the DC circuits, this theorem can be applied to the AC circuits which contain linear elements such as resistors, capacitors and inductors. Similar to equivalent Thevenin's resistance, equivalent impedance can be obtained by changing all voltage sources through their inside impedances. Which theorem is applicable for the linear and nonlinear circuits? Substitution theorem is applicable for linear and nonlinear circuit. How do you use Tellegens theorem? Tellegens theorem can be used to design the filters and complex operating systems. The applications of Tellegens theorem include the following. Tellegen theorem is used to examine difficult network systems like electrical circuits, metabolic and biological networks, chemical processes and pipeline transport networks. Tellegens theorem is used to design filters in the digital signal processing DSP system. Used in biological and chemical processes. Used in reaction network structure analysis and topology. Used in different oil and chemical plants to determine the complex system's stability. This theorem is applicable for the circuits which have linear-nonlinear, time-variant-non-variant, and active-passive elements. Thus, this is all about an overview of Tellegens theorem, derivation, example problems, and its applications. The limitations of Tellegens theorem are, for Tellegens theorem verification, KVL and KCL equations are used. This theorem mainly works on the law of energy conservation principle. This theorem is used in a number of network systems. Conclusion: Bernard Tellegen was the first to point out 1952-1953 the generality and wide-ranging usefulness of the theorem that bears his name. Nevertheless, the theorem is still not as widely known as its utility warrants. The authors of this monograph set out to correct this neglect, noting that there is hardly a basic network theorem that cannot be proved by invoking Tellegens theorem. The simplicity and generality of the theorem make it attractive pedagogically, and its ability to generalize known results and lead to new results indicates its research value. This theorem definitely should be in every circuit designer's kit of tools. Tellegens theorem is unusual in that it depends solely upon Kirchhoff's laws and the topology of the network. The theorem thus applies to all electrical networks that obey Kirchhoff's laws, whether linear or nonlinear, time invariant or time variant, reciprocal or non-reciprocal, passive or active, single-valued or multiple-valued, hysteretic or non-hysteretic. The excitation is arbitrary. It may be sinusoidal, exponential, periodic, transient, or random. Also, the initial conditions may be arbitrarily chosen. The modern interest in nonlinear and time-variant networks gives Tellegens theorem a special new importance, because it is one of the very few general theorems that apply to such networks. To demonstrate its range of applications and the theorem's great power in the derivation of other basic and important theorems about electrical networks and the extent that these other theorems are special cases of Tellegens, the authors have collected more than 100 such theorems and have shown that they can be proved from Tellegens theorem. Most of these were known before, but some are extended in their range of validity, and a few are new. Apart from Tellegens theorem, this collection of theorems is valuable in its own right. Applications are given to automated network synthesis and to nonlinear, time-varying, switching, non-reciprocal, and other networks. All the major areas of network theory are covered. In addition, extensions of the theorem to other physical systems are discussed, including applications to the electromagnetic field, electron beams and plasmas, and quantum mechanics. The theorem is proved in its most general form thus far known. In addition, two weaker forms that have useful properties for certain applications are presented. In these weaker forms, the theorem applies to voltages, currents, and wave or scattering variables. The use of wave variables in Tellegens theorem is believed to be new.